One of the trickiest things about machine learning is finding the best hyperparameters to use when training your model. If you're not familiar with the concept, hyperparameters are all the little settings you need to configure that's not part of the model itself. This can include things like learning rate, the number of nodes in a layer, and the batch size. Reinforcement learning in particular is very susceptible to small variations in hyperparameters. A difference of 0.0001 in your learning rate may mean the difference between a working AI agent and one that just sits there doing nothing. If you have a deep understanding of the training algorithm, you can often tune these hyperparameters yourself, but there are also tools to help us automatically find such values. In this episode, I'll show you how to use Meta's Adaptive Experimentation, or AX, framework for tuning hyperparameters. We'll apply it to the inverted pendulum problem from my previous reinforcement learning video to find a model that works well. Note that you can use hyperparameter optimization tools like AX or weights and biases on any number of tasks, including basic supervised classification machine learning. I just think reinforcement learning is cool, so that's what we'll be focusing on. Let's jump in. Hyperparameter optimization often follows a pretty simple loop. First, we choose a set of hyperparameters for our model and training methods. We then train the model and then test it against some known test set. Finally, we log the chosen hyperparameters along with our test scores. We repeat this process over and over again until we find some hyperparameters that work for us. However, figuring out which hyperparameters to choose next is the difficult part. For simple ML models, this can often be done by hand. But for complex models or tasks, like reinforcement learning, this could involve dozens of parameters with little insight into their effectiveness. The easiest approach to this is to try all combinations of reasonable hyperparameters. Let's say you are working with just two sets of hyperparameters, learning rate and, say, batch size. You can list all reasonable values of each and lay them out on a grid like this. Notice I said reasonable. It still requires some human insight to figure out what exactly is reasonable for a particular task. You could do a much wider search and then begin to narrow that search space as you learn more. But for now, let's just go with this. You do one iteration of that loop with one set of hyperparameters. You train the model and then test it. You repeat that process for the next combination of hyperparameters, and so on, until you've tested all possible combinations. From there, you just find whichever model performed the best and retrain it using those hyperparameters. This approach is known as grid search. While it's exhaustive and accurate, it's often very time-consuming, especially when you have many hyperparameters or training the model can take a long time. Another option is to randomly sample a few of your possible hyperparameter combinations and test with just those. You can then do some math to estimate a good possible combination, even if that combination was not drawn in the random sampling. As you can probably guess, this is known as random search. While it's more efficient than grid search, it can also take a lot of time if training your model takes hours or days. There's one more popular approach which uses Bayes' theorem to iteratively make an informed guess about the nature of the function that provides model test results given some hyperparameter values. You start by picking a hyperparameter combination at random and training the model on that. Based on that, use Bayes' theorem to choose the next set of hyperparameters. The arbitrary approximation function will slowly get better at figuring out which hyperparameters will yield better test results. So, we continue this loop until we reach an acceptable optimum with the best test results. Most modern machine learning applications will start with grid or random search to figure out an acceptable range of hyperparameters and then use Bayesian optimization to fine-tune them. We'll stick with just Bayesian optimization for this demonstration. Lucky for us, we don't have to compute Bayes' theorem by hand. Meta's ACTS framework can do that for us. I'll be demonstrating this in Google Colab because it makes it easy and you don't have to install anything. So log into colab.research.google.com and you should be presented with a screen like this. We need to install a few packages. I'll first install Gymnasium, which provides our environment for our reinforcement learning pendulum. In this case, it's just a virtual environment. We'll also install Stable Baselines 3 for doing the actual reinforcement learning. That's the PPO algorithm that comes from there that we will use. We will install Meta's ACTS platform and weights and biases, which will help us log and visualize what's going on with the training. Note that I'm pinning all of these versions because you can very quickly end up in dependency hell. And so I know that these versions worked for me. Hopefully they will work for you. When that's done, I often like to check the versions to make sure everything installed properly. We'll check the versions of PyTorch, Gymnasium, Stable Baselines, and ACTS, which we just installed. OpenCV should come installed in Colab, so you don't need to install it, but if you're trying to run this locally, note that you will likely need to install it. Sure enough, these should match the versions of the packages that we installed here, so if we scroll up, double check those. Yes, everything looks like it's been installed correctly. There are a good number of packages that we need to import into our project. We'll start with the usual suspects: time, datetime, OS, random, logging. All of these are standard Python packages that will help us. I also like to use typing, especially when we're creating our own classes and functions, which we will be doing, as it allows us to specify the type of any parameters or return values. Next up is our third-party packages. Notice how I'm grouping these together. The standard packages I like to put at the top, and then a space, and then our third-party packages. We'll import Gymnasium, Matplotlib, NumPy, Torch, CV2, which is OpenCV, and the weights and biases package. Then I'll group together the imports for Stable Baselines 3. We're going to need our base callback because we're going to be stopping training every now and then in order to test our agent, and that's what we're going to log to weights and biases. We'll also want to create our own custom logger to help us create a weights and biases logger. From ACTS, we're going to import the ACTS client, optimize, render, and then train and evaluate. With any luck, these should all import without a problem. Next up, you'll want to call wandb.login, which allows you to log into your weights and biases account. Here, it will ask you to paste in an API key. So if we go to this site, if you have not done so already, it will ask you to log into your account. You can see I'm already logged in here, and it's going to display an API key. Just copy it to your clipboard, and then we're going to paste it right here. Hit enter, and with any luck, you should see true, which means you are now logged into weights and biases. The wandb package has a habit of being very noisy when you're logging things, especially if we're doing lots of trials and experiments. It's going to flood your outputs with a lot of useless information. So I like to make wandb be quiet. To do that, you first need to set the environment variable wandb_silent to true, and then also set the wandb logger to just the logging.error level. Next up, we're going to create some helper functions. Random seeds in reinforcement learning can make a difference between getting an agent that works and doesn't. There's a joke in the reinforcement learning community that says your seed is one of your hyperparameters. To ensure that things are repeatable, we're going to set as many of the seeds as we possibly can so that we can replicate what happens during our training process. The three basic packages that we're using that use some sort of randomness, there's the internal Python random package, there's NumPy, and then there's Torch, so we'll all set the seeds for those. If you're training on a GPU, you're likely using CUDA, and CUDA has its own randomization functions that Torch relies on. So if you're using CUDA with Torch, then you need to set the seed, or you need to set CUDA to be deterministic. And to do that, we just set the backend's CUDNN deterministic to true for Torch and set the benchmark to false. Next, we're going to set up our reinforcement learning environment. and we're going to do that inside of Gymnasium. If you watched my reinforcement learning co-op video, you saw how we created an entire custom Gymnasium environment. This time we're going to use one of the built-in Gymnasium environments known as pendulum v1. To do that, you just call gym.make and give it pendulum-v1 and give it the string pendulum-v1 as an argument. We're also going to set the render mode because we want to record this so we can watch the pendulum at least when it succeeds. If you're curious, I'm going to put the documentation for this here. This is the Gymnasium documentation for the pendulum environment. Feel free to look through this. I talked about this at the end of the Intro to Reinforcement Learning video, and I gave it to you as a challenge. But in that challenge, I said you're welcome to look up known good hyperparameters. This time, we're going to find our own hyperparameters to solve this environment. Back in our Colab script, we're going to run this. It's going to create that Gymnasium environment for us. You can get a sense of how to control the environment if you start playing with some of the functions. For example, end.reset gives us an observation and information about the environment, and it also resets the environment to a known good starting place. I believe for the pendulum, it's actually randomized the position that the pendulum starts in. You can see that our observation is 3 values that correspond to the x and y position of the pendulum's free end and the angular velocity of the pendulum. There's also no extraneous information that's passed from the environment. Next, we're going to get one of the frames from that environment, and we're going to use that to calculate the width and the height of the frame. This will help us render the environment when we're testing it. Then, just for fun, let's show that frame using matplotlib. With any luck, we should see our pendulum in a space here, and it should print out the shape of that frame, which is 500 by 500, and 3 channels because it's RGB. Next, we want to create a function that will test the model in its given environment. We'll pass in an environment, a model, and this will just perform the tests for us and spit out test results. The first thing we do is reset that environment, just like we did earlier, and set some of the metrics we want to collect to 0, such as the episode length, the episode reward, and the average step time, which is useful for figuring out how long it takes for things to execute in our environment and with our agent. Then we'll just let our agent do its thing with the environment, and we'll just run it until complete. The easiest way to use a trained model, or one that's in the process of being trained, is to simply pass the observation to the .predict method. That will give us a predicted action, and I believe in a value output, but we don't need to worry about that right now. That action is what happens in the environment, and then we collect a reward based on how the environment responds. We'll use the Gymnasium environment to actually perform that step for us. So we just pass in that action that we got from our model, and it's going to spit out the observation reward, whether the environment has terminated or is truncated, and any extraneous information. I'm going to keep track of the average step time because it's one of the metrics I want to track. We accumulate the reward because each reward comes from an individual step. What we care about is the total reward for an entire episode, which is after all the steps have run. Then, if we have a video object that's been passed into this function, we will want to record a frame to that video object. To do that, we will render the frame from our Gymnasium environment, and then we will use OpenCV to first convert the color from RGB to BGR, because OpenCV does everything in BGR. We then call the cv2.putText function, where we pass it in the frame text to add, where that text should be in the image, the font scale, the color, the thickness of the font, and the line type to draw with. Once we've added that text, we will write that frame to the video object. We will then increase our step counter, and if our step counter goes beyond the maximum allowable steps for this particular episode, we will go ahead and end the episode. Similarly, if terminated or truncated comes back true from our Gymnasium environment, once again break out of the while loop. We then take our accumulated average step time, divide by the episode length, in order to give us the average step time for that episode. And finally, we return the episode length, episode reward, and that average step time. In lieu of having a trained model that we can use to test some things in our environment, let's create a very quick dummy agent. All it will do is just spit out a random action regardless of whatever observation you give it. Next, we want to define our recorder settings and create that video object, much like we did in that Intro to Reinforcement Learning video. Then we're going to run a few episodes with our dummy environment and see how it performs with random actions. So we'll let that go. After our 5 episodes, you can see our reward is not that great, and you can go ahead and download that file. Remember, we named it 1-random.mp4. If you download that and open it, sure enough, you can see the episodes just kind of doing some random actions here. The arrows show the action that is being taken. It's essentially showing which direction the pendulum is being pushed and with how much force. Next, we want to set up the testing and logging callbacks for stable baselines 3 that will be used to test our agent as it progresses in its training and logs things to weights and biases. We'll create a function to evaluate our agent. We can pass in a model that has any amount of training during the training process. We'll initialize the metrics. We'll test the agent using that test agent function we created earlier. And we will accumulate the episode length, episode reward, and that average step time. And then we will average each of those by dividing those accumulated values by the number of tests we plan to perform. And then we'll return those metrics from this function to be used in logging. Next, we're going to subclass the base callback class that's found in stable baselines 3. It expects a number of particular inputs, including the check frequency, which is how often we're going to perform this callback, where to save any checkpoints, what to name the model, if we want to rename the replay buffer, which we're not going to do in this case, and then we're going to define the number of steps per test, the number of tests to perform, a step offset, and whether to print stuff to the console. So we're going to call our constructor and just set all of those fields to the provided argument values. Next, we'll want to define the init callback method. Note that this naming is very specific because somewhere in stable baselines 3, this function is looked for and called whenever you instantiate your subclass. So at the beginning of training, it will find our callback and call specifically init callback. In this case, all we're going to do is make sure that a directory is available for us to save our checkpoints in. If not, create that directory. Next, we're going to define what happens every single step. So our callback is actually called every step. This is the known onStep function. But then we only execute the rest of it if nCalls, which is a field inside of the object that gets updated on every step. So we have access to that, and that's n_calls. And then we compare that to our check frequency, say every 10,000 steps. The rest of this gets executed, and that's where we'll want to create our checkpoints. Then we'll add any sort of offset to the number of calls, and then save that model into our known good checkpoint directory. Some of the reinforcement learning algorithms that you find in stable baselines 3 have this thing called a replay buffer, where it saves the last known number of steps, including observations and rewards. And in order to pick up where you left off, it needs access to that. So if there is a replay buffer, we should go ahead and save that along with our model. So at the very least, we can pick up where we left off if, say, your script crashes. A lot of times you'll find you'll run these scripts for hours or days on complex reinforcement learning tasks. And if something happens, you need to have a save point, essentially. During each one of these checkpoints, we should go ahead and evaluate the agent so that we know how well it performs. And we can always go back to one of the models in that agent because we have saved it to our disk. In this case, all we're going to do is just call that evaluate agent function that we created earlier, pass it in the environment, the model, and the number of steps per test and number of tests we wish to perform. We'll also log some stuff to the console if we want to enable verbose mode. In addition to calculating those metrics, we also want to log them to weights and biases. This is actually fairly simple. All we do is construct a dictionary with the name of each metric, the value of each metric, and then we pass that dictionary to the wandb.log function, We'll set commit equal to true, which actually uploads it to our project on weights and biases, and we give it a step count so it knows what the x-axis is. And then we just return true because stable baselines expects a true return from on step to let it know that everything succeeded. And it looks like I have an error. Some type of indentation problem. Okay. Aha. These all need to be indented 1. Hopefully that works. Yep, all good. Next, we want to log some things to weights and biases. We'll do that by subclassing the KV writer that's found in stable baselines 3. We'll initialize the run and just save our run and verbose settings to some class members. Next, we'll define our write function to write things to our weights and biases project. I'm going to use some typing hints here to ensure that the caller passes in the correct types of values to key values, key excluded, and the step. Next, we want to go through each of the key value pairs that are passed into us and make sure we don't log anything in that key excluded item set. Let me make sure my indentation lines up correctly, because that is important in Python. Everything's 2 spaces in Colab, so I'm going to make sure everything's 2 spaces in Colab. So this is part of this function. After this for loop, this should be lined up with this for loop, and we're good. And if we have logging enabled, we will print all of that to console. Finally, if we call the close function, that will just close out the weights and biases run. Finally, we get to the interesting stuff where we can define our training and testing functions for a single trial. So a trial is one set of hyperparameters, and we're going to train an agent and evaluate it along the way. We'll wrap everything up in this doTrial function, and we'll start by setting the random seeds like we talked about earlier. We'll then create a new weights and biases run. So every time we do a trial, we get a new weights and biases run within a single project so we can compare the different runs. We'll name the run based on the current UTC date and time, and then we'll call wandb init in order to create that run. We'll also print the wandb run info to the screen so we can verify that new runs are being created. Next, we want to assign our custom weights and biases writer to one of the loggers for stable baselines whenever it's going through its training process. Notice that I'm using the hparams dictionary in order to store the hyperparameters. That becomes a lot easier to log, manipulate them, and use Axe to modify them. There are a few where we want to derive the actual hyperparameters from some setting. For example, the number of steps or the layers we may want to be a power of 2. That seems to be common practice when constructing, say, neural networks. That can also potentially help with calculation optimizations if you're using, say, like a GPU or an accelerator. The PPO algorithm in stable baselines 3 wants the mini batch size to be some factor of the total number of steps, which is the number of steps per environment times the number of environments. And environments are parallel running environments. In this case, we're just going to keep environments to 1 to keep things simple. But we first calculate that total number of steps and then divide it by some divisor. In this case, it's just 2 to the power of this batch size divisor power 2. We then also calculate the number of nodes in each neural network layer, and we're only setting those first 2 layers. And we're going to constrain this to a 3-layer network, but the 3rd layer is automatically calculated for us, so we're just setting the first 2 layers. Right now, I don't have a good way to pick up trials from where they left off, so we generally just want to restart a trial. So for that, I'm just going to keep that to 0, knowing that we have to restart trials if something happens. That's not too bad for what we're doing. Here's my attempt to pick up a trial from where it left off. I try to load the model file from that checkpoint dir. But I never quite got this working. For now, we'll always just start every trial anew. So when we're creating that new model, we're going to use the PPO algorithm from stable baselines 3. We'll always use a multi-layer perceptron policy, so we'll set that as our network. We'll also pass in the new environment, and then we'll go through our various hyperparameters that we want to set. For example, the learning rate, the number of steps that we want to train for, the mini batch size, gamma, entropy coefficient, whether we want to use SDE or not, and if so, how often to sample that, And then in the policy kwargs, we can define the network architecture. This is where we actually set the layer 1, layer 2, those number of nodes. And then finally, we set the verbose value, which we get from our hparams, which I need to correct. Nope, that is settings. Just like we did with that weights and biases writer, we want to set up our checkpoint callback. That's the one we wrote earlier. And we'll pass in the settings in order to configure that. Let me correct this one parameter issue that I had. That should be good. And this is the magical function here that tells the model to actually start learning. Notice that we have to pass in our callbacks here, and I'm passing in that checkpoint callback. Next, we want to get the history of our metrics from that particular ID. Using that entire history from the previous run or that trial, we're going to go through that and find the one that gives us the maximum average episode reward. Once we know that, we can then test with that one. To assist with that, we're going to find the number of steps to produce that maximum reward. And that information is going to be used to load the correct model that we have saved from our checkpoints. Here's where we actually load that model. We go back through all of the checkpoints that we had created, look through that directory, and then load the model that gave us the maximum reward during training. To evaluate the agent, we're just going to call that evaluate agent function that we created earlier. And it looks like it's giving me some type of bug here. What is going on? Let's scroll up and figure out what is going on. Oh, because I can't spell. Evaluate agent. There we go. Thank you, Colab. Oh, and I forgot to run that cell. Don't forget to run your cells. Where is it? Here it is. All right. That should be good. Once we evaluate the agent, we should have the average episode length, average episode reward, and average step time. We'll just go ahead and log those final evaluation metrics to that particular weights and biases run. If we have verbose turned on, we'll go ahead and print all of those final run metrics. And then we'll go ahead and close that weights and biases run so that we can start a new one in the next trial. And then I'm going to return the average episode reward from this function so that we can use that later. Let's start by defining the settings that we don't want to change. This essentially defines all the things about our project. We'll give the weights and biases project a name. We'll call it pendulum X HPO for hyperparameter optimization. We'll name the model, which is going to be used for those checkpoint file names. We'll give the experiment a name in X as well as an objective name. This objective name is what we're trying to optimize for. In other words, we're trying to find hyperparameters that optimize our average episode reward based on testing of each of the models that we have trained. We'll give our replay buffer a name, which there is none for PPO. We'll also create our checkpoints directory and how often we want to do that checkpoint. In this case, every 10,000 steps, we will save that model in a file in that checkpoints directory. Then we'll say we want 100 steps per test and 10 tests per check. That occurs every time we create a checkpoint. We'll define the total number of training steps, which is 100,000, and the number of trials we want to perform when we evaluate our model. Finally, a good old seed of 42, because, it's the answer to the life, universe, and everything. We will turn off all of our verbose settings except for trial. We do want that to be printed. Then we finally start defining the hyperparameters that we want to optimize. This is what Axe is going to look at when it's going to pick from some range, and those hyperparameters will be used when creating the model when we defined it in that doTrial function. As you can see here, this is where it's pulling those from. Axe will choose that for us, so we just have to define the hyperparameters using a very specific set of dictionary keys. If you go to axe.dev/docs/api.html, you can see the API documentation for the Axe framework. If you scroll down, you can see where these parameters are defined, and you can dig into this to see what these keys should be. For now, we're going to set the number of environments to 1. That's going to be a fixed value, so this is not something that Axe can vary. However, feel free to play with these if you'd like to try multiple environments as one of your hyperparameters. Next, we're going to set our learning rate. This is a range between our two values 1 times 10 to the minus 5, all the way through 1 times 10 to the minus 2. We're going to set log scale because generally we find that learning rate is more sensitive to orders of magnitude rather than individual values. And I'm just going to copy and paste these blocks to make this next part a little easier because I have to fill out a lot of different hyperparameters. Next, we'll define the steps per update, which is the number of steps the environment will take before the training algorithm updates the model. This is one of those cases where having a power of 2 can be helpful. So rather than setting the actual step value, we're just going to say it's 2 to the something. And we're going to say something between 6 and 12, and that's inclusive. So 6, 7, 8, 9, 10, 11, 12 are possible values for this hyperparameter. And then it's a derived value, so it actually becomes 2 to the n. So for example, 2 to the 6, that's 64 steps per update. Or all the way through 2 raised to the power of 12, which is actually 4096 steps. This is where we set that divisor for the batch size, and it can be something between 1 and 8. It's 2 raised to some power. Next, we'll define gamma, which is the discount rate when the agent is trying to predict the future gained rewards by looking out from the state that it's in. I recommend referring to my Intro to Reinforcement Learning video if you'd like to learn more about that. This is-ordered key is only really useful when you have a collection of values to choose from, so we don't actually need it here. I'm going to go ahead and get rid of it. And then let's keep defining other hyperparameters. Oh, what is wrong with my indenting? There we go. I gotta fix all of this. It would still work. It just bugs me. All right. So I copied in 2. So we'll start with this second gamma. And we're going to define the entropy coefficient to be something between 0 and 0.1. Some of these are based on gut feeling or what I've seen used in similar models. So we just kind of define a best guess range and go from there. Once again, this is where something like grid search or random search can help you narrow your focus. And now we're going to use Bayesian optimization to pick the exact values within these smaller ranges. This is where that is-ordered key comes in, where we have a choice between, in this case, 2 different values. And Axe needs to choose one of those rather than figuring out some value within a continuous range. SDE is short for Generalized State Dependent Exploration, and it's one of the ways PPO can figure out how to explore rather than exploit a given policy. We can turn SDE on or off, and if it's on, we can choose an SDE frequency. And if I go to the PPO documentation, where you can see the hyperparameters here, -1 actually means to only sample at the beginning of a particular rollout. Okay, so that's a possibility if we are using SDE. Power of 2 things. And this is our first layer. And then we will do our second layer, which is basically the same thing. Note that one of the interesting things about Axe is that you can set parameter constraints. So you could say that like layer 2 must be greater than layer 1 and it has to obey those. But we don't have any, so we will just leave that empty for now. Just like we saw before, we're going to create our environment. Well, actually first try to close it if it's already open from our tests earlier. Then remake that environment exactly in the same way that we saw earlier, where we're going to use the pendulum 1 environment and we'll set render mode to RGB array. One of the things I did earlier was set the Axe experiment name as one of our settings. We're going to save the experiment after every trial. That way, if something happens during training or during our trials, we can go back and at least redo the previous trial that we were on. We can essentially pick up where we left off. I'm going to leave this here. If you uncomment this os.remove axe snapshot path, you can delete that experiment file if you want to start completely over. But if you leave this commented, we're just going to pick up where we left off, or create a new one if there is no snapshot. This is where we'll say if that path exists, go ahead and load it from the JSON file. And if that file doesn't exist, go ahead and create a new Axe client. This is to run our hyperparameter optimization. We'll set the seed and verbose settings from our settings dictionary, and then we'll create an experiment in that object. Here we'll give it a name, set our hyperparameters. Notice we're passing in that entire hyperparameters dictionary that it's going to read in and figure out what it needs to choose. That's coming from this list of hyperparameters up here. Then we'll set the objective name, which in our case is the average episode reward, and we'll set minimize to false because this is not a minimization problem. We don't want Axe to find where the smallest reward is. We want Axe to find where the biggest reward is. So hence minimize is false since this is a maximization optimization effort. And then finally we'll pass in those constraints, which if you remember, we don't have any. With any luck, we should see creating new experiment snapshot saved. However, values are required for choice parameters. Ooh, I messed something up. Values are required for choice parameters, so it's one of these choice ones. So it can't be bounds. This needs to be values. The key was wrong. So don't forget to run that cell, and let's try creating that experiment again. All right, no errors, some info, but that's fine. And snapshot to be saved in this JSON file. We're good. And this is where all the magic happens for doing actual hyperparameter optimization. We will essentially run forever, but we want to do axeclient.getNextTrial. That will do the Bayesian optimization to figure out which hyperparameters we should choose next. Notice here we're getting next hyperparameters and then the next trial index. We'll compare that trial index to our maximum number of trials that we want to complete. And if it's over or equal to that, we're going to go ahead and end this optimization with all the experiments. We'll go ahead and print the new trial index whenever we're starting a new trial. We'll call that doTrial function, where we pass in our settings, which don't change from trial to trial, and the next hyperparameters that we got from Axe. After that trial is complete, where we train an entire agent and then test the best model from that agent, remember it returned the average episode reward. That's the value we're trying to optimize for. So we call axeclient.completeTrial. We pass it in the trial index as well as that average episode reward that we just calculated. From there, on the next iteration, it will call getNextTrial, and it will give us the new trial index and hyperparameters. And that cycle just continues until we're done. We've reached the maximum number of trials we want to do. The last thing I want to do is, after every single trial, save our client information to this snapshot so that if any of this breaks, we can just reload that snapshot and pick up from where we left off. Let's go ahead and run this. With any luck, you should see a new trial being printed. You should see a weights and biases ID and name. This should be a date and timestamp. And hopefully that's going. While that's going, I'm going to log into weights and biases, or wandb.ai. On my dashboard, I should see the new project that I just created, Pendulum Axe HPO. Let's click on that. We can see the trial that's being run here. This is going to take a little time because there's lots of training, lots of testing, lots of experimentation to do. And that's a single trial, and I believe we have 30 trials. So here we go. Metrics are starting to roll in. We can view some system information about what's going on here, the network traffic, the disk utilization. If you're using a GPU, you'll see GPU power and GPU heat, and that's just going to continue until the end of the experiment. These are logged in seconds, and as the agent is trained, you should see that logged in steps. We'll get a new one up here. So let's just wait a little while and come back to this once this is done. Okay, things have stopped, and it looks like I've got an error here. This is quite useful. So model name, we need to figure out where I probably misnamed something. Model name is not defined, so it's probably in my settings. Model underscore name. Okay, that is defined here. So is something not getting passed in? What is happening? So it's the on-step self.modelName. Okay, so model name is a problem right here. We don't want to save model name, we want to save model path. Okay. Let's save that, run through these again, because somewhere that callback gets assigned to something, so I want to make sure that these get run again. Notice here we create a new experiment because this JSON file did not save, and let's try again. Make sure it logs into weights and biases, trial 0 starting up. So this is where things get interesting. Notice that in weights and biases, this trial crashed. Not really crashed, it didn't complete. I recommend only keeping completed runs in here, so I'm going to go ahead and get rid of this one. Let's delete that run. So now we just have the new run that's happening, and we're going to let that run for a while. Let's check back in a few minutes. We got a little farther, but it looks like we've got another error, so let's come back to here. Oh dear, what is going on here? Do trial. What is happening? Distribution, stable baselines, it doesn't like the shape of something. Looks like we probably have a divide by 0 problem. After carefully going through the code, I found something. It looks like when I evaluate the agent, yep, there is a misspelling here. So that's probably not great. And I need to run through these one more time, because while looking at the code, the runtime disconnected for me. So we want to test these, perform trials all the way down here. And let's see if this runs a little better. So after making that spelling fix, we're going to try to run the experiments again. And I'm going to wait for a little while and see what pops up in weights and biases. We don't need that window anymore. And in just a second, I should get a new trial. There it is. And so I can delete this old one. And let's wait for just a moment. After doing a lot of digging, I found hopefully something that will lead me in the right direction. If we take a look at the error, the not a number leads me to believe that there's probably something being divided by 0, something going to infinity. It could be an exploding gradient or any number of issues. This one's actually really tricky to track down. To help with that, I have found a way that we can log some metrics. If we take a look at the logger API docs in Stable Baselines 3, we can log any number of these just by calling a particular function and feeding it a key value that would be like train/clip_fraction. This will give us some insights into what's going on. So back in our training script, we're going to go to where we log values, which is up here, the eval. So this is where we're logging metrics to weights and biases. And rather than write them one by one, I'll copy them in. As you can see, we're just doing the self.model.logger name to value train / and then the metric. And that lines up with train / the metric we see here. Here's all the information about those metrics if you care to get them. Everything I read said that this is likely exploding gradients. And so rather than digging into the algorithm itself and then potentially trying to narrow down some of those hyperparameters, we want to keep going with hyperparameters. So what I'm going to do is just change this total steps to 50,000 to prevent those gradients from exploding over the course of time. Remember, we're just using this to find some hyperparameters that should work for us. So let's give this a shot. Let's make sure that we have run our new logging, which is up here. This is this cell. Okay, so we'll run through these again. And Let's see if this works for us. We're going to go over to weights and biases. There's our new run. We're going to get rid of the old run, refresh the page, and now we wait. It looks like training is done. We've got 30 trials here. The thing to look at is the average episode rewards. As you can see, these later trials, they all go up, and a lot of them even pass minus 200, which is really good. In fact, we can turn some of these off, visualize none, and go back to some of the earlier ones. And you can see none of them really start learning. It's only once we get past these few trials, I noticed something in the 15 to 20 trials, that we actually start to consistently get good agents that learn over time. The other thing I notice, if you go to the train metrics, the standard deviation of the noise when using generalized state-dependent exploration, that's the thing that would explode after about 60 or 70,000 steps for some of the hyperparameters. So right now, it's 1 to 4. That's really not too bad. It would quickly go up to 1 times 10 to the 18th. And that was giving us a divide by infinity or some large value that couldn't be represented. So keep an eye on that when you're training. This is a good metric to watch to make sure something doesn't get way out of control. So what we're going to do now is pick one of these that looked really promising, like this yellow one, which is down here. We're going to go to this run, and we're going to go to overview. These are the hyperparameters that were used to make that work. Notice that we turn SDE off here, which is a good sign to potentially prevent some of that exploding standard deviation. In fact, for this next part, I'm feeling lucky. So I'm going to go back to training a full 100,000 steps. With that, we're going to come up here, enter a new section, and we're going to fill out the hyperparameters from that particular run. So here's my learning rate. I'm going to copy that. And there is a programmatic way to read all of those metrics from weights and biases, but I'm just feeling lazy right now. So let's just get them manually. Steps per update, power of 2. That was 10. What is that? Batch size divisor. Looks like 2. Figure out what our gamma is. It's 0.9 value. Let's copy that in. We want that entropy coefficient, which is right here. I do remember seeing that being false. Yes, indeed. This shouldn't matter because SDE is turned off. Set it to 7 anyway for good luck. What was that first layer? Looks like they're both 7. And we can ignore that warning for now. We're going to create our environment like we've done before. And we're going to train our agent again, but we're going to do so for 100,000 steps using the hyperparameters that we got from our weights and biases experiments. So if we go over here, we can go back to our project. And here's our new run. This one should go for 100,000. So we will wait for that to complete. Our agent is done training. It looks like it didn't perform quite as well as that initial test, but this should be good enough. We would probably want to continue with our experimentation and trying different hyperparameters, but it trained fairly well. It looks like it's hopefully going to work. Let's find out. So we'll create our final section here. And this is where we want to find the best model. It looks like it's the second to last one, so 90,000. So if we go into checkpoints, sure enough, PPO pendulum, 90,000, not the 100,000. It's not always the last one. And we will define the model file name and video file name for our output. And as we continue to do, we'll create our environment again from scratch. We'll then load the model, which is going to come from this 90,000.zip file. As we did before, we'll use OpenCV to create a video writer so we can see the output of this test. I'm going to go ahead and make this a little bit more readable. We'll write to every frame the model file name that we're using, so that should be the 90,000.zip. And we'll print those metrics to the console so we can see how well the model performed. And when we're done, we'll close the video writer. Let's run it. Ooh, that is not a great reward. Minus 400. What happens if we run again? Does it perform a little better? And let's see what happens when we open this. And it's trying to get the swing up. It's oscillating some, so it's really not that bad. It should hold it there. Let's try a different hyperparameters. Something that looks pretty promising, like this red one. This maroon one here. Go to Overview. So batch size divisor is 2. Good. Entropy coefficient is this 0.05. Gamma is 0.9. And so we have 6 and 7, which is interesting. Or 7 and then 6. Learning rate is 0.01. Seems kind of high. STE frequency is 6. Shouldn't matter because use STE is still false. And then steps per update is 10. Let's try running that again. See if we can get a little bit better of a model. So let's go back to our runs. We have our green run here. Once again, looking kind of promising. So that 70,000 mark is supposed to be the best. So we're going to load that one. And let's see how it performs. Solidly worse. Nice. Let's see what it does. Okay. It actually successfully holds it there. So it looks like more work is needed to continue to test these. And what I should have been doing is continuing all these tests out to 100K. But we can continue going. Instead of 30, we can keep going to 50. In fact, I'm going to do that and then come back to this. So let's go up to here. And I'm going to run a few more tests. Let's try to keep it at 100,000. See if it works better. If not, I'll drop that down to 50,000 again. You'll notice that when we do this, it actually loads from the checkpoint. Oh, sort values is not specified for choice parameter. Let's go ahead and make that change, avoiding errors or warnings when we can. So up in here where we've got use SDE is ordered, that ordered parameter should take care of this. Maybe there's a different version of ax. Now let's try this. See what happens. It's kind of a weird bug. Sort values is ordered, both are false, and it's still yelling at me. Okay. Alright, well, we tried. This might be a weird bug. Oh, and the last thing we want to update is number of trials. Let's take this to 50. We're going to keep going where we left off. You should really run all the trials to the same length, 100,000 steps instead of 50, but I like living dangerously. Let's see what happens. Here we go with trial 30, and I'm going to go ahead and delete these two tests. So once those are deleted, let's refresh this page. And we will let this run for a while. After we've gone for about 50 trials, we have some here that look pretty promising. What does this one go to? Minus 134. It's this latest one. This one goes all the way up. That looks pretty good. So let's try these. So entropy coefficient. So we're going to come down here. This is basically the same, so it's converging to some good values. Here's the gamma. 6.6. Here's the learning rate. That doesn't matter too much. And then steps per update power of 2. Let's go to 11. All right, let's see if this trains a little better. And we will come right back. Let's go to our new trial and see what happens. All right, so this one finished here. And it didn't do too bad. Minus 153, that's pretty solid. So 70,000 again. We're going to change this. Yep, 70,000. We'll let this test. Hey, that looks pretty good. Minus 127. Let's download it. And we'll take a look. All right, so it's still oscillating a good bit, but it is keeping it up in that upright position. And there it swings up, and it's holding it there. I'm pretty happy with this result. Let's call this good. The pendulum doesn't work quite as well as I have seen it done before, which makes me think we're in a local maximum for the hyperparameters. So what I recommend, if you are up for a challenge, is to actually perform something like random search prior to doing Bayesian optimization, and to also let these run for a longer period of time. Ideally, doing something like random search will narrow down your scope before doing Bayesian optimization, and that should get you something closer to a global maximum, which allows you to pick even better hyperparameters. But for now, hopefully this is a good enough demonstration. I focused on ACTS to perform hyperparameter optimization locally, but note there are other tools out there. Weights and Biases has its own optimization framework called sweeps. You can configure Bayesian, grid, and random searches similar to what we did in ACTS. I hope this helps you get started with hyperparameter optimization to build your own AutoML pipelines. Good luck and happy hacking!